High school math can sometimes seem like this jumble of ideas that don't really go anywhere. You may ask your teacher, when am I ever going to use this? And he may, or may not, provide you with an answer that satisfies you. Well, we are going to get into a few of the big ideas of high school math and look over why they are important in other areas, not just for your next test. It may be hard sometimes to trust that these courses are going places, to deep, complex, beautiful places. Some of those places are in your other classes, and some you have yet to encounter. Many of the concepts you touch on in class are exhibited every day in the real world, and in the world of video games. This photo is of a Lorenz attractor, which is basically a model created to predict the climate and weather. There are 4 main mathematics courses taught in high school: Algebra 1, Algebra 2, Geometry, and Trigonometry. Sometimes you take Calculus or Statistics as well, but I'm only going to touch on those since they aren't taken as often by students. Each of these subjects requires you to learn things that don't really seem to have a point when you take them. Matrices are great examples of things that take a while to get awesome. It isn't really clear to most students why they insist on you putting numbers in a little cluster to perform operations, other than rotating shapes. Well, matrices can be used to solve systems of equations with multiple variables, and they've been used for that purpose for more than 2,000 years. In algebra, you learn about equations: linear, quadratic, cubic, quartic, and so on. These equations never really go away in math, so you might as well get comfortable. One place these equations become really useful is when you learn about linear regression. Don't worry, it isn't as intimidating as it sounds. Linear regression is all about finding the best line to approximate a scatterplot of data. Still intimidated? Think of this example. Your teacher does a poll on the day of your next test. She asks you to write down the number of hours you spent studying. Then she puts those figures on the x-axis with the score you received on the test on the y. When she plugs in all of the data, she can see if overall the class received higher grades from studying longer and how large of an effect studying has. Now, if you're getting skeptical right now and thinking there's a whole lot of other factors that affect test scores, you're thinking like a good researcher, scientist, and mathematician. Some of the most important uses of mathematics are in fields that may not seem directly related to math. Even though we don't like to admit it, math is everywhere. Another thing you learn is the quadratic formula, and whether you learn it from a song or a rhyme or you just remember it, chances are that you used it to find the roots of most quadratic equations you encountered in algebra. Well, one thing you may not know is that the quadratic formula is derived from completing the square. This derivation isn't usually explained because it relies on some concepts that you haven't covered yet. In geometry, you begin to learn about proofs. The frustrating thing about this is that some curricula have you translating, rotating, and reflecting shapes. Then they teach you how to prove congruency. Then they move on to more drawing of shapes. Learning this method of proof is crucial to mathematics in college. For example, in a course called Analysis, you look at all the aspects of calculus and you prove them. You may be thinking that you've already proved things and it couldn't be much harder. However, if you've taken calculus, you know that proving limits isn't always the easiest thing. Now imagine if you had to prove that the formula for finding limits actually worked. That is analysis. It's a cycle of asking questions, explaining the answers, and then asking more questions. And that's how new areas of math get discovered. People ask questions and try to prove things as rigorously as possible. Then sometimes they find out that things didn't quite work out the way they had planned. For example, in Euclidean geometry, which is what you're taught for most of school, one postulate says, given a line and a point not on it, there exists exactly one line through the point which does not intersect the first line, no matter how far it's extended. However, when we look at elliptic geometry, which is based on circles and ellipses, lines need to go around the full circle and come back on themselves and cut the ellipse in half. So if we think of the round world we live in, we know this postulate doesn't hold. It's also important to note here that, by definition of line on a sphere, most latitude lines are not mathematically lines. Rigorous proofs may seem really difficult, and that's okay. Even if we aren't working with proofs, sometimes trying to explain your answer can be really difficult. You want to just put an arrow to all of your work and say, there, that's why it's true. And then teachers have to settle for having you write a complete sentence that includes the answer, and that does nothing to tell you why it's important, or tell the teacher that you understand why the answer is right. So if proofs or explanations seem really tough, try to remember that math is based on logic, not numbers. As a matter of fact, the more math you take, the less of a role actual numbers play. Like in this mathematical statement, you end up dealing with lots of variables, like x, y, epsilon, delta, for all there exists. Now, some school districts don't offer trigonometry as a separate course from pre-calculus, so in those cases, trigonometric functions are just sort of squeezed into the coursework. And your teacher may make you memorize the unit circle and SOHCAHTOA, and you're probably sitting there wondering, what do these ratios have to do with anything that I should be caring about? Well, You may have seen the sine curve before. It has a period of 2 pi radians and oscillates between -1 and 1. It's okay if that didn't really make sense. It's like a slinky or a spring that is pulled out and looked at from the side. Just like many other equations, the sine curve goes off to infinity in the direction of the x-axis, but the point of the ratio and the sine function itself is much more interesting. These curves are used in the modeling of behavior of liquids like water. If you drop a pebble in the water, it ripples out. The curve would look a little like a regular sine curve, except since we know that ripples get smaller and smaller as they get farther, we would actually need a sine curve whose height is smaller each new crest that is reached. Now we need more equations. These curves are also seen in music. Each time you draw the bow across a violin, for example, sound waves move out from the instrument to our ears. The pitch of each sound has a unique frequency. Without getting too technical, we know that we can write the mathematical equation of each note that is played on the violin, and consequently represent music with a series of mathematical curves. So that about covers some of the big ideas. We talked about matrices, linear regressions, scatter plots, elliptic geometry, parallel postulate, quadratic formula, completing the square proofs, trigonometric functions, and waves in water and music. Hopefully you've seen that some of these ideas are teaser trailers for future courses, but they all have value in the real world we live in. I've already spoken a little about the place of math and music, science, and English, and I hope you can see some of the applications I didn't mention, like math and art. If you have no idea, go exploring. I encourage you to, and look for these connections in the real world. Thank you for your time and attention. And remember, enjoy math.